In this exercise, we are asked to write out each of these four sets explicitly by listing every element of the set in curly braces. So our first set is the set of all odd integers between 0 and 8, namely 1, 3, 5, and 7. Our second set is the set of all days of the week not containing the letter N. So that's Tuesday, Thursday, Friday, and Saturday. All others contain an N. Our third set is the set of all X such that X was a wife of Henry VIII. So if you know your history, you'll know there are 6 wives of Henry VIII, and they are as follows. So this is a set containing 6 elements: Catherine of Aragon, Anne Boleyn, Jane Seymour, Anne of Cleves, Catherine Howard, and Catherine Parr. Finally, our fourth set is the set of all X such that X starred as James Bond in the official series of films. Again, this is a set containing 6 elements. The set consists of Sean Connery, George Lazenby, Roger Moore, Timothy Dalton, Pierce Brosnan, and Daniel Craig. And there are all 4 of our sets written out explicitly. And we're done. In this exercise, we're asked to write out these 2 sets explicitly by listing their elements inside curly braces. So let's take a look at the first set. This is the set of all X such that X is an integer with X equals 2Y, where Y is taken from this set of the integers 1 to 5. So any element of this set is of the form 2y, where y is one of these integers. So we can list these out. If y is 1, then double it to get 2, which is an integer, and so it's in this set. If we let y be 2, then 2y is 4, which is an integer, and so it's in this set. If we take y to be 3, then we get x is 6. If y is 4, then we get x is 8. And if we take y to be 5, then x is 10. And this is a complete list of integers that can be found by doubling one of these numbers. And so that's our complete set. Now let's take a look at the second set. This is the set of all X such that X is an integer with 2x equals y this time, where y is again taken from the set of integers 1 to 5. So this time, any element that is in this set is of the form half of one of these numbers, right? Since any of the numbers in this set can be doubled to get one of these numbers. And also keep in mind that every element of this set is an integer. So let's think about what numbers we can double to get one of these numbers. Well, to get 1, we could double a half. But a half is not an integer, and so it's not an element of this set. To get 2, we can double 1, and 1 is an integer, so 1 satisfies this condition. 1 is an integer with 2 times 1 equals 1, which is in this set. Okay, to get 3, we could double 1.5, but that's not an integer, so it's not in this set. To get 4, we can double 2, and 2 is an integer, so it's in this set. To get 5, we would have to double 2.5, which is not an integer, and so we're done. We have found every integer that can be doubled to get one of these numbers. So we found the complete set, and we're done. This exercise asks which of these propositions about set membership are true. So let's take a look at A. Is 2 an element of this set? That's pretty straightforward, right? This set contains the elements 1, 2, and 3. So yes, the number 2 is one of these 3 elements. Now B says the set containing the single number 2 is an element of the set containing 3 numbers, 1, 2, and 3. Well, no. This set on the right does not contain a set containing the number 2, right? So this is false. Now, C asks whether the set containing the number 2 is an element of this set containing 3 sets. Well, yes, it's right here, right? The set containing the number 2 is one of these 3 elements of the set on the right. D, is the empty set an element of this set? Well, no, this set on the right is the empty set, so it contains nothing, does not even contain the empty set. Okay? Whereas this set in E is the set containing one element, namely the empty set. So yes, the empty set is a member of this set. This exercise asks which of the following propositions about set inclusion are true. Remember that inclusion is different to membership in that we are comparing two sets and asking whether each element of the set on the left is a member of the set on the right. Okay? So let's take a look at A. Is the set containing the single element 2 included, is it a subset of the set containing 3 elements, numbers 1, 2, and 3? Well, each element of the set on the left, namely the one element 2, is a member of the set on the right. So yes, this is true. Now let's take a look at B. Is the set on the left, the set containing 3 numbers, 1, 2, and 3, a subset of the set containing 3 singleton sets? Well, no. For example, this element 1 is not contained in the set on the right, or rather it's not a member of the set on the right. The 3 elements of this set are singleton sets, right? So this is false. Now let's take a look at C. The set on the left contains one element, namely the set of 1 and 2. And the set on the right also contains one element, the set containing numbers 1, 2, and 3. So we are asking whether each element of the set on the left, in this case there is only one, is this element a member of the set on the right? Well, no, it isn't, right? Because the element here is a set containing 2 numbers, and this is clearly not equal to the one element here, which is a set containing 3 numbers. So, again, this is false. In this exercise, we examine an interesting set. R is defined as the set of all x taken from the set A, such that x is not a member of itself. So x does not contain itself as an element. Now the question is, does R contain itself? Is the set R a member of itself? Well, suppose it is. Suppose R is an element of R. Well, then this tells us that R must satisfy the condition that it is not a member of itself. So this is a clear contradiction. So this tells us that in fact we must have R is not a member of itself. Now it may seem that now that we have this fact, this tells us that R is a member of itself, since it now satisfies this condition. But actually, all this tells us is that R is not a member of the set A, since this set contains only those x that are in A and satisfy this condition. So this is not a paradox. The solution is that R is not a member of itself, and R is not a member of A. In this exercise, we're given 3 subsets of a universal set, and our task is to use these 3 sets, as well as the operations union, intersection, and set difference to construct this set of three elements. Now, a useful thing to do is to draw a Venn diagram depicting these sets to help us visualize them. Now, looking at these sets, and we want to construct the set containing 1, 3, and 7, we can see that these values are all in the set C. So the set that we want to construct is exactly the set C, but without the values in this section. And what is this section exactly? Well, it's the intersection of A and B. So the set we're looking for is the set C minus the intersection of A and B. And we can write this using our set operations. This is the set we're looking for. And we're done. In this exercise, we're given three subsets of a universal set. Our first task is to draw a Venn diagram depicting these sets. First, let's think about what goes in the center section. So these circles represent the sets A, B, and C. So this section will contain any value that is in all three sets. And in this case, that is just the number 5. Next, let's think about this section. So here, the sets A and B overlap. So anything that is in both A and B, but not C, will be contained in this section. Looking at our sets, we can see that 3 is in A and B, and not C, and that's it. Next, let's think about this section. So here, the sets A and C overlap, but not B. So that's 7 and 9. Now, this section would contain anything that is in both B and C, but not A. But actually, the only thing that is in both B and C is the value 5, which we already have in the diagram. And so this section will be empty. Now let's fill in the rest of set A. Only the value 1 is left, so that's set A complete. Next, let's fill in the rest of set B. So we already have 3 and 5, so all that's left is 4. And finally, let's fill in the rest of set C. We already have 5, 7, and 9. So what's left? 6 and 8. Now there's one thing left to do, and that is to add in all the values that are in the universal set, the universe of discourse, that are not in any of these three subsets. So that is the values 2 and 10. And there is our complete Venn diagram. Our next task is to compute these 5 sets, and we can use our Venn diagram to help us here. So first, A intersected with C. So we're looking for any value that is in both A and C. So any values that are in this section where A and C overlap. So that's 5, 7, and 9. Our next set is the intersection of A and B union C. So that is anything that is in both A and B, as well as anything that is in C. So A intersected with B contains 3 and 5, this overlapping section, and C contains everything that is in C, 5, 6, 7, 8, 9. So this set contains all the values that I just listed. Next, we have the intersection of A and B union C. So we're looking for any value that is in both the set A and the union of the sets B and C. So the union of B and C is all of this section, and A is of course just A. So the intersection of these two sets will be this section containing 3, 5, 7, and 9. Next, we have the set A union B minus the set C. So A union B contains everything that is in either A or B, but we are removing anything that is also in C. So we're removing 5, 7, and 9 from the union of A and B, and we're left with 1, 3, and 4. And finally, we have this set, which is the intersection of the complement of A union B with the set C. So the complement of A union B is everything that is not in the union of A and B. So here's the union of A and B. The complement is every value that is not in that section. So that is 2, 6, 8, 10. And this set that we're looking for is that set, 2, 6, 8, and 10, intersected with the set C. So we have 2, 6, 8, and 10, and we take all the values that are also in C, 6 and 8, and that gives us this set. And we're done. In this exercise, we form the power set of the set friends, which is a set of 4 elements. Now remember, the power set of a set is just the set of all subsets of that set. So we need to find all subsets of size 0, all subsets of size 1, all subsets of size 2, and so on. So let's start by thinking about subsets of size 0, subsets that have no elements. Well, that can only be the empty set, which is a subset of any set. So there is one subset of size 0, the empty set. Next, let's think about subsets of size 1, so subsets that have one element. Well, there are 4 elements of the set friends, and a set that contains exactly one of these elements is a subset of the set friends. So the set containing just Dan is a subset of friends. As is the set containing just Eve, and the set containing just Mia, and the set containing just Tom. And that is all the subsets of size 1. Next, let's think about subsets of size 2. So subsets that have 2 elements. Well, that could be any 2 of these 4 elements together, right? Any 2 of the 4 elements form a subset of size 2. So, for example, we could have a subset that contains Dan and Eve. And that is one subset of size 2. Or we could have Dan and Mia. Or Dan and Tom. Or Eve and Mia. Eve and Tom. Or finally, we could have a subset containing just Mia and Tom. And these are all the subsets of friends of size 2. Okay, next let's think about subsets of size 3. So that is any set that contains 3 of these elements and nothing else. So we could have the set containing Dan, Eve, and Mia. The set containing Dan, Eve, and Tom. Or Dan, Mia, and Tom. Or finally, the set containing just Eve, Mia, and Tom. And there are our subsets of size 3. What about subsets of size 4? Well, there is exactly one subset of size 4. That is just the set containing all 4 of these elements, the set friends itself. And there can't be any subsets with more than 4 elements, since the set itself only has 4 elements. So we're done. And this is the power set of the set friends. So we have one set of size 0, 4 subsets of size 1, 6 subsets of size 2, 4 subsets of size 3, and 1 subset of size 4. And that's it. This exercise involves forming different power sets. Remember, the power set of a set is just the set of all subsets of that set. So we are given the set A, which is just a set of one element, and our first power set to form is the power set of A. So first of all, there is one subset of size 0, that is the empty set. The empty set is a subset of any set. And there is another subset that is the set containing A. That is a subset of this set. And that is all subsets. Next, we want to find the power set of B, the power set of the set that we just formed. Okay, so we're looking for all subsets of this set. So first, let's think about subsets of size 0. There is one of those, the empty set. What about subsets of size 1? Subsets of one element. Well, B contains 2 elements, and so there are 2 subsets of size 1, namely the subset containing the first element, the empty set, and the subset containing just the second element. So there are our 2 subsets of size 1. And there is one more subset, the subset of size 2, which contains both of these elements. And there we have the power set of B. Now, the next power set to form is the power set of C. That is the power set of the set that we just formed. Now, this could get a bit messy, so let's make this easier for ourselves by labeling the 4 elements of C. Okay, so I've defined 4 variables, right, that match the 4 elements of the set C. And this should help us to form this power set. Okay, first, let's think about subsets of size 0. Again, there is one of these, one subset of size 0, that is the empty set. Next, what about subsets of size 1? Well, there is the subset containing just the element W, which is the empty set, so the set containing the empty set. Then there is the subset that has just element X. So that's the set containing just X. And then there is the subset with just Y. And the last subset of size 1, the set containing just Z, containing just this element. So that's one subset of size 0 and 4 subsets of size 1. Next, let's think about subsets of size 2. So first there is the subset that has W and X. That's one subset of size 2. So this set has W and X. Next, there is the set that has W and Y. Then there is the set that has W and Z. So that's 3 subsets of size 2. We can keep going. There is the set that contains X and Y. Then the set that contains X and Z. And finally, the last subset of size 2, the subset containing y and z. And that is all the subsets of size 2. There are 6 of them. 1, 2, 3, 4, 5, 6. Next, let's find all the subsets of size 3. So first of all, we have the subset that contains w, x, and y. Then there's the set that contains w, x, and z. W, x, and z. Next, we have the set containing w, y, and z. So that's now 3 subsets of size 3. And there's one more, the set containing x, y, and z. That's nearly all the subsets. There's just one more. We have one subset of size 4. That is the set containing all 4 of these elements, w, x, y, and z. And this is the complete power set of C. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 subsets of C. And we're done. Computers have to represent data in some format. For example, rational numbers can be represented as ordered pairs of integers. The rational number x over y is represented as the pair xy. But in order for this to work, we have to be able to apply the same operations on both representations and get the same result. In this exercise, we define the operations of addition and multiplication on ordered pairs of integers so that they correspond to the same operations on rational numbers. So let's start with addition. Now, when we add two rational numbers, we first give them a common denominator. In this case, to do that, we would multiply a and b by d, and c and d by b, and then we can add the numerators to give our result. Now we can just convert all of these rational numbers into their representations as pairs, and that will give us the definition of addition on ordered pairs. That's how we define our addition. Next, let's look at multiplication. Now, multiplication of rational numbers is a bit simpler. We just multiply the numerators and the denominators. And again, we can simply convert all of these into their ordered pair representations to give our definition of multiplication. And we're done. In this exercise, we examine possible ways of representing ordered pairs using sets. Now, it clearly doesn't work to just use this representation. This is because sets are unordered collections of objects. So, for example, these two different pairs, 1, 2 and 2, 1, would be represented by the same unordered set. So we're going to have to be a bit more clever about this. Consider this representation. Here we represent the ordered pair xy as the set containing two sets. One, the singleton set containing just x, and the other, the set of two elements, namely x and y. How do we know if this is a good representation of the ordered pair? Well, we know that two ordered pairs should be equal if and only if their first coordinates are equal and their second coordinates are equal. If this is true of our set representation, then it is a good representation. Now, if we use this set representation for an ordered pair, then we know that these two ordered pairs are equal if and only if this set representation of the two pairs are equal. And the only way this is possible is if the two singleton sets contain the same element and the two sets of two elements contain the same elements. And so this is only possible if x is equal to u and y is therefore equal to v. Which is exactly what we wanted. So this representation works. We can use this representation for an ordered pair. Let's consider another possible representation. Here we try to represent the ordered pair xy by the set containing x and the set containing y. This might seem to work as a representation, at least better than this one does. But consider this pair. This is the ordered pair with first coordinate the set containing just 0 and second coordinate the number 1. The representation of this pair using this definition would be a set containing two sets, which are the set that has just 0 in it and the set that has just 1 in it. But this also represents a different ordered pair. That is the pair with first coordinate the set that has just 1 in it and second coordinate the number 0. These two ordered pairs are different, so their representations as sets should be different. So this shows that this representation does not work. In this exercise, we revisit our old friend Lewis Carroll, who, upon reading these three statements, deduced that no baby can manage a crocodile. Our task is to model the situation using sets and a Venn diagram, and thereby come to the same conclusion. Now I've defined 4 sets for us to use in this exercise. B, the set of babies. I, the set of illogical people, D, the set of despised people, and M, the set of people who can manage a crocodile. Now, the three statements give us three relationships between these sets. So let's take a look. A says, all babies are illogical. In other words, B, the set of babies, is a subset of the set I, the set of illogical people. Now statement B tells us nobody is despised who can manage a crocodile, right? In other words, the intersection of the sets D and M is empty, right? Because nobody can be both despised and manage a crocodile. And finally, statement C, illogical people are despised. So this tells us that the set I is contained in the set D, right? I is a subset of D. So let's use these relationships to draw a Venn diagram, right? Start with the set B is contained in the set I. Which itself is contained in the set D. And finally, we have that the intersection of the sets D and M is empty, right? So nothing can be in both the set D and the set M, right? But now it's clear from the Venn diagram that no one can be in both the set B and the set M, right? In other words, no baby can manage a crocodile. After reading these 7 statements, Lewis Carroll concludes that Amos Judd loves cold mutton. Let's see how he gets there. The first statement is, all the policemen on this beat sup with our cook. In other words, the set of policemen is a subset of the set of people that sup with our cook. Secondly, no man with long hair can fail to be a poet. In other words, every man with long hair is a poet. Or the set of men with long hair is a subset of the set of poets. The third statement is that Amos Judd has never been in prison. In other words, Amos Judd is an element of the set of people that have never been in prison. Statement D is, our cook's cousins all love cold mutton. Another way to say this is that the set of the cook's cousins is a subset of the set of people that love cold mutton. Next, none but policemen on this beat are poets. In other words, all poets are policemen on this beat, or the set of poets is a subset of the set of policemen. Next up, none but her cousins ever sup with our cook. So everyone that sups with our cook is the cook's cousin, or the set of people that sup with our cook is a subset of the set of the cook's cousins. And lastly, men with short hair have all been in prison. Another way to say this is everyone that is innocent, that is, everyone that has never been in prison, has long hair. Since men with short hair have all been in prison, everyone that has never been in prison must have long hair. Or the set of people that have never been in prison is a subset of the set of men with long hair. Now let's put all this information together and see if we can make a conclusion. First of all, statement C tells us that Amos Judd is an element of the set of people that have never been in prison. Now what else do we know about the set of people that have never been in prison? Well, statement G tells us that it is a subset of the set of men with long hair. Now statement B tells us that this set is a subset of the set of poets. And statement E tells us that the set of poets is a subset of the set of policemen. The set of policemen is a subset of the set of people that sup with our cook. This is from statement A. Then statement F tells us that this set, the set of people that sup with our cook, is a subset of the set of the cook's cousins. And statement D tells us that the set of the cook's cousins is a subset of the set of people that love cold mutton. So now we can see that since Amos Judd is an element of the set of innocents, he must also be an element of the set of people that love cold mutton. Amos Judd loves cold mutton. A survey is being carried out to find data on the types of pets people own. Now we are going to model the results of the survey using a Venn diagram and then use this Venn diagram to find some information on our data. Okay, so let's draw some shapes. Here we have a set C representing all cat owners, and set D representing all dog owners, and set O representing all owners of other non-traditional pets. So, what information can we fill in? Now, we have that there are 3 people who own a cat, a dog, and a non-traditional other pet. Okay. Now, let's take a look at this subset. This is all those who own both a cat and a dog, but not other. So, 11 people own both a cat and a dog. 3 of those also own a different pet. So that leaves us with 8 who own just a cat and a dog. Here we have those who own a cat and a different pet, but not a dog. So 9 people own a cat and another pet. 3 of those also own a dog, so we're left with 6. And here we have dog and other owners, of which there are 8. 3 of those also own a cat, so we're left with 5. Now, this set contains all those who own a cat, but no dog or other pet, right? So there are 25 cat owners total, and 17 of those own other pets. So that leaves us with 8 people that own just a cat. And similarly here, we have 26 dog owners, and now 16 of those also own another pet. So that leaves us with 10 people own a dog and no other pet. And finally, we have 26 owners of other pets, 14 of which also own a cat or a dog, leaving us with 12. Now, the information that we want to extract from this diagram is the number of people that own a pet and the number of people that own exactly one pet. Right, so for the first piece of information, all we need to do is add up all the numbers, right? And I make that 52 pet owners total. Now for our second piece of information, the number of people that own exactly one pet, we are omitting the subsets where we have overlap, right? Because all of the people in these subsets own multiple types of pet, right? So 8, 12, 10, I make that 30. In order to work out who won this game, we need to work out how many countries appear in each of the indicated sections of this Venn diagram. Now, we're told that the 3 people listed 12 countries in common, right? There were 12 countries that all 3 listed. Felix and Oscar listed 23 countries in common. Now, 12 of those were also listed by Amanda, which leaves 11 in here. We're told that Amanda listed 7 countries that were not on Felix's list. And since Amanda listed 22 countries total, this leaves 15 that both Felix and Amanda listed. Now 12 of these were also listed by Oscar, which leaves 3 to go in here. Now Amanda listed 9 countries that were not on Oscar's list. 3 of these were also listed by Felix, which leaves 6 that were uniquely listed by Amanda. We're told that Felix listed 29 countries total. Now adding up what is in Felix's circle so far, we get 11 plus 12 plus 3, which makes 26. So that leaves 3 countries uniquely listed by Felix. And finally, we're told that there were 13 unique countries listed total. And we have 6 by Amanda, 3 by Felix, making 9, which means that Oscar must have listed 4. Now we can finally see that Amanda was the winner of this game.